This topic has already been introduced, Chapter 13, Gases. So today, we're going to do a little review, and we're going to use the CENGAGE homework. Of course, the problems that were not assigned to you to do, these are extras, but they are the same type of problem. So in order to do that, I need to share the CENGAGE homework website, which is right here. And there it is. Okay, I think that's big enough to see. I don't think there's really any way I can expand that. Maybe do it like that. Okay. So what I've done, I've started off by picking out of this left-hand section, started off with difficulty level 1. So these are going to be really, really easy things to kind of get us rolling. And this first one is 13007. All right, so here's what they want us to do with that one. Simple conversions. Okay. So here you're talking about dimensional analysis. In other words, you need a conversion factor. So this first one, A, they want us to convert 38.1 kilopascals. 38.1 kilopascals to atmospheres. Okay. Yeah, that's the wrong place there. Let me write it about here. Okay, so how do we do that? Well, you need a conversion factor that will cancel kilopascals and leave you with atmospheres. So the conversion factor is how many atmospheres is a kilopascal, or how many kilopascals is one atmosphere. So we look, you look in your textbook, or you can look in useful information. That's with your review document, or this review document that's in Blackboard. And in the back of it, useful information, it will have that conversion factor. Let's see. 1 atmosphere. All right. We don't have kilopascals, we have pascals. So now you have to say, if 1 atmosphere equals 101,325 pascals, how many kilopascals is that? Well, remember, if the size of the unit gets bigger, then the number has to get smaller. So a kilopascal is 1,000 times the size of a pascal. That means this one has to decrease by 1,000 times. 1, 2, 3. So it's 101.325 kilopascals. In 1 atmosphere. So now all we have to do is crunch the numbers. Calculator out. All right. 38.1 kilopascals divided by 101.325. And that's 0. Let's see, 3 positions, 0.376. Atmosphere. Okay, So let's put that one in. 0.376. Submit. That one's good. Let's move down to the next one. So what does B say? B wants us to convert 711 millimeters of mercury millimeters of mercury to atmospheres. So what's the conversion here? Millimeters of mercury to atmospheres. How many millimeters of mercury is 1 atmosphere? You can look that one up too, but I happen to remember it. 760. So should the number be greater than 1 or less than 1? That's 760, that's 711. It should be less than 1, right? .936. All right, so let's put that one in. And submit that one. All right, likes that one. All right, so I'm gonna start over here for C. So I have a suspicion it's gonna need a chained conversion. 757 torr. All right, and we want to convert that to kilopascals. Oops. All right. So we've got the conversion here for atmospheres and kilopascals. Why don't we convert this to atmospheres and then the atmospheres to kilopascals? So what is a torr? A torr is the same as a millimeter of mercury. So 760 torr equals 1 atmosphere. All right, that cancels torrs and leaves us with atmospheres. Now we need atmospheres. Here is on the top. We need atmosphere on the bottom. But that's valid, isn't it? All conversion factors are equal to 1. So if you flip it, it's still 1. So that's kilopascals. 101.325. Okay. All right, so the rest is crunching numbers. 757 divided by 760 times 101.325. And I get, let's see, 3 significant figures would be 101 kilopascals. So let's see if the system likes that answer. It appears they do. All right, one more. Let's see. Convert 1.11 atmospheres to millimeters of mercury. That's a simple one. 1.11 atmospheres to millimeters of mercury. So what's an atmosphere? 760 millimeters of mercury. So we just say 760 times 1.11. So I get 3 significant figures, right? These significant figures, I don't say they don't count. These are exact numbers. In other words, they have infinite significant figures. So we're only focusing on this one. So 3 gives us 844 millimeters of mercury. All right, we got them all right. So now let's go. Let's see if the next difficulty level 1 is the same type of animal, or if it's something different, then we'll stay with it. Let's see, convert this many pascals to atmospheres, pascals to atmospheres to pascals. It's the same type of animal. The only difference is that first one is in scientific notation, which is no big deal because your calculator will handle it. So let's skip down. Let's see if this number 1 has something different for us. All right, what volume of gas would result if 120 milliliters of neon gas were compressed from 106 atmospheres to 2.74 atmospheres? Okay, this is a good one. So let's make room. Okay, and let me straighten things up here. There we go. All right, so this is 13.021. All right. Now, the question is, what volume of gas results? But we're already given a volume of gas, aren't we? We're given a volume of gas as 120 milliliters of neon. Right, of neon. And it wants the volume after we do something to it. So what's the, it's also given before and after pressure, right? That's the key question. What type of problem is this? Is this a before and after problem, or is this a state problem? If it's a state problem, then we would use the ideal gas equation. If it's a before and after, then we would use one of the gas laws or the combined gas law. So it looks to me like we've got, what's the pressure to start with? 1.06 atmospheres. And what's the pressure afterwards? 2.74. Okay, it's important that we put this information up here with the proper variables assigned to it, because this volume is associated with that pressure, and this volume is associated with that pressure. If you don't do it that way, then when you write the equation, you could put the numbers in the wrong place and get the wrong answer. So V1 is 120 milliliters. P1, excuse me. Well, P1 is here, 1.06 atmospheres. Then P2 is 2.74 atmospheres. And V2 is the unknown. So we solve for the unknown. We just say this one times that one divided by this one. And we get the answer. So let's see. And notice we don't have to change the volume to liters here, because this is a before and after problem. The volume here cancels the volume here, the units. Right? So we have the same units here as we do here. The only time you need to convert, well, there are two times when you need to convert. One is always temperature, has to be converted to Kelvin. And the other time is if you're using the ideal gas equation, then you have to convert to conform with the ideal gas constant. But we'll get to that. There will be problems like that coming up in a few minutes. So with three significant figures, I've got 46.4. Milliliters. Okay, so let's plug that in. It wants the answer in milliliters. Notice that right there. So let's put it 46.4 and submit. And yes, it did enjoy that answer. All right. So let's see what's next. That's the whole thing. And check our position. That's good. All right. So let's see if this one is any different. 022. Let's see. We have liters. If the pressure on a 1.03 liter sample of gas is doubled at constant temperature, what's the new volume of the gas? Okay. This is worth looking at. 13.022. All right. So this sounds like a before and after problem. If the pressure on a 1.03 liter sample, that's the initial volume. What's the pressure? Doesn't say. It just says what happens to the pressure. So we can pick anything. The volume is this is the new volume. This is the question. The second pressure is actually 2x. It says double the pressure, and the temperature is constant. So if we're going to double the pressure, let's see if we can stick those values into the formula and find the answer. All right, so it's P1 V1 equals P2 V2, and we're solving for V2. So let's just go ahead and solve for V2. So that's P1 V1 over P2. Okay. So let's put in what we know and see if anything shakes out. P1 is X. V1 is 1.03 liters. P2 is 2x. Okay? All right. So X is canceled, correct? X is canceled. Leaves us with 1.03 divided by 2, which should be, let's see, 0.515 volume in liters. So let's put that in. And it liked it very much. All right. Have to keep repositioning this board. It likes to walk on me. Okay, let's see if this one is any different. 023. A sample of helium gas with a volume of 21.8 milliliters at 782 millimeters mercury is compressed at constant temperature until its volume is 12.6 milliliters. What's the new pressure? This is the same thing. Before and after, you just have different substitutions. So I don't see any sense in doing this one. It's just repetition. Let's try the next one. 1.48 liters of argon is cooled from 288 to 72 K. What's the new volume? Okay, now we've got a different gas law, but is this before and after or a state? Well, it says 1.48 liters is cooled from one temperature to the other. That's a before and after. All right, so this is 035. By the way, the problems we've worked up to this point, the before and after problems, welcome.
Sorry, I was having internet issues.
Okay, understood. It's all recorded.
Yeah.
Excuse me. I'm down to 13.035. We've covered unit conversions, simple unit conversions now, and we had a couple of problems based upon Boyle's law, pressure and volume. Now this problem is volume and temperature, which is which one? Charles' law. So what does Charles' law say? Charles' law says that this one is equal to this one. Okay? So, what do we know? 1.48 liters is the beginning volume. And the question is, what's the new volume? So we know the beginning temperature, and they're nice enough to give it to us in Kelvin. Right? That's why it's difficulty level 1. You don't have to convert. It's already in Kelvin. 288 K. And the new temperature, the gas has been cooled down to 72 K. That's pretty cold, right? 0 degrees, freezing, is 273 K. Right? So that's pretty cold. That's 200 degrees cooler. All right. Argon gas. Okay. It's not quite cold enough to liquefy argon, but it's pretty cold. Okay, back to the problem. So now we want to solve for this one. This one stays here. That one goes over there. Now we can substitute values. 1.48 liters. T2 is 72 K. And T1 is 288 K. So that's the thinking part. Now we just crunch numbers. And I get 0. Let's see, two significant figures here, so 0.37. liters. All right, let's see if the system likes that answer. It did indeed. That was Charles' law. Volume and temperature. And of course, with each of these individual laws, remember, to describe a gas, we need to know pressure, volume, temperature, and moles. And for any two of these to be defined in relationship, the other two have to be constant. Excuse me. So let's go down and see if this one is any different. Let's see. 378 milliliters is heated from 35 to 62 at constant pressure. What's the volume of the sample at higher temperature? Okay, the only reason I'm going to do this one is because we have unit conversions that are required. So 13.037. This is also Charles' law. So what are we given? 378 milliliter sample of neon gas. And the question is, what's the volume of the sample at the higher temperature? So that volume is at this temperature, 35 degrees. And we're going to raise the temperature to 62 degrees. Notice that the temperature is given in Celsius, so we have to convert it. Right? So that would be 803, okay, and this would be 5, 7, 13, 335 K. Notice the difference here. Excuse me. The ratio between this one and this one is about 2. You just about doubled, not quite, doubled the temperature in Celsius, but over here you have not doubled the temperature. That's why if you use these values, you get an answer that's wildly wrong because the ratios are different. All right, so what's the law? V1 over T1 equals V2 over T2. So we're solving for V2. V1 times T2 over T1. Right, so the first volume is 378, and they want the answer in milliliters, so we're just going to leave the volume where it is with those units. And then the second temperature is 335. And the first temperature is 308. So now comes the easy part. So I get 3 significant figures, 41.1. No, 411. Watch my decimal place. 411 milliliters. So does that make sense? If we heat the gas up, the volume should increase. And it does. Put that one in. And it likes it. Let's see what's next. That was 3743. If this one's any different. This one is different. 13043. All right. Is this a before and after? Excuse me. 1.52 moles of argon occupy a volume of 136 liters at a given temperature and pressure. What volume does 15.90 moles of argon occupy under the same conditions? Yes, we have changed the number of moles. We want to know what the new volume is. We are holding pressure and temperature constant. This is Avogadro's law. Okay, so let's put down what we know. We've got 1.52 moles of argon is the initial moles. We're going to pump that up with more moles of argon gas. And now the total is 15.90 moles. The beginning volume with that many moles is 136 liters. We want to know what's the volume after we pump in all that extra gas. All right, so Avogadro's law says that this volume at that many moles would be equal to this volume at that many moles. So if we solve for this one, we have V1 times N2 over N1. So we'll just put in the numbers. 136 liters, 15.90 moles divided by 1.52 moles. And I get let's see, three significant figures. Excuse me. 1423, 142. Actually, 1420 will be rounded off. I'm going to keep that extra one there, just in case. All right, so they did limit it to three significant figures, which I should have done. Fortunately, the built-in error range allowed my answer to be accepted. All right, let's see. There we go. All right, let's see. We got another one here. Difficulty level 1. Let's see if it's a different type. What mass of neon gas is required to fill a 1 liter container to a pressure of 1.29 atmospheres at 27 degrees? All right, this is a different problem. What type of problem is it? Are we given before and after conditions? No, we're told what it is right now. and we want to know the mass of neon under these conditions. So, do we know a gas law that will give us mass? Nope. We know one that'll give us moles, right? Let's write down what we have. 1 liter of neon. Okay, let me get 051. 13.051. All right, so we have neon gas, and we have a volume of 1 liter. And let's see, we have 1.29 atmospheres. And we have a temperature of 27 degrees. You know that temperature is going to have to be converted, so we might as well do it now. So that's 0, and that's carry the 1, that's 0, that's 300. Okay. Okay, so all we can do at this point is find out how many moles of neon there are. Then we have to do a conversion. So what's the equation? Right? So we know everything but moles, right? Do we know what R is? Well, if you don't remember what it is, it's right here in the useful information. And the units tell you which one to use. Liter, atmospheres, mole, K. That means R has to be, well, let's put in the others also. 1.29 atmospheres, volume of 1 equals moles times 0.08206, and temperature is 300. I left the units out just to save space. So if we solve for this one, that is that one times that one, divided by that one, divided by that one. So 1.29, 0.08206, and 300. So I get, let's see, 5.24 times 10 to the minus 2 moles. Now we can determine the mass of neon because we have moles. Right? We just need a conversion factor. Remember, whenever you have grams and moles in a quotient, one divided by the other, you're talking about molar mass. So what's the molar mass of neon? Well, just look it up. It's right here in our table. Neon, 20.18 to 2 decimal places. Okay, so the mass now is, I've already got that number in my calculator, so I'll just multiply it by 20.18. And I've got 3 significant figures, 1.06 grams. Let's see if the system likes that one. There we go. Okay, that took a little bit of extra effort. Got a frog in my throat this morning. Okay. All right, let's see. That looks good. Let's see what the next one has. Let's see. This is kind of the same problem. It might be useful to work it. So we have to decide first, if we're given, the question is what volume? If you have 5.73 grams of helium and 97 degrees Celsius, 743 millimeters of mercury, right? What volume will that occupy, right? Is that a before, after, or a state? That's a state function. That's PV equals nRT. So O53 we're going to need this one. And what do we have? 5.73 grams of helium. So we have mass. Right? We can't work with that. It's got to be moles, doesn't it? All right, we'll do moles in just a second. Let's put everything else up here. Temperature. 97. All right, we're going to have to convert that too. And pressure. That one's got to be converted also. Why? Because our units of measure are liter atmospheres per mole K. That's not atmospheres. Now we can make atmospheres. How about this one? We got to convert helium to moles. So what's the molar mass of helium? Well, it looks to me like it's 4.00. Okay, so we got some preliminary values to determine. 5.73 divided by 4 is 1.43. I'm going to keep an extra decimal just to avoid rounding errors. 1.4325. Okay, this one's going to be 370. Okay, this one's going to be 743 divided by 760 is 0.9776. Atmospheres. Okay, so back to the question. What will be the volume? Right? Take that equation, solve it for volume. All you have to do is move the pressure over here into the denominator. Now we can put moles. Universal, or the ideal gas constant. Temperature, 370. And divided by pressure in atmospheres. There we go. So let's do those numbers. All right. So I want to 370 times that one. And then 0.08206 times that one. And then 0.9776 divided. So I get 44. Let's see, originally we had 3. Let's say that was 3. 3. Let's keep it to 3. 44.5. What are the units? Liters. 44.5 liters. If I did my calculations correctly. I think it likes the answer. So that one took a little bit of extra effort. You have to be sure before you can use that ideal gas equation, your units are correct. So we had several conversions to do. All right, let's see. Not doing too bad there. Okay, let's scroll down and see if there are any other ones that are of a different nature. What pressure exists in a 130-liter tank containing 7 kilograms of neon gas at 291? All right. This is a state problem. It uses the universal, or the ideal gas equation. Liters, it's already got liters volume. It's already got temperature for in K. It's got neon in kilograms, right? You can't convert kilograms. It has to be grams. That's 7,000 grams. Convert that to moles. Then you can solve for pressure, right? So I don't need to do that one. Let's see if we can find a new one. Level 1. Are there any more level 1s down here? I think we're out of level 1s, right? So we'll go to level 2, difficulty level 2. Now let's go back to the top. Let's see, did I make it all the way to the top? Yep. So there's difficulty level 2. All right, let's see what this one has to offer. Oh, okay. I think we got a winner here. This is, well, this one doesn't have a number. Chem work, manometer pressure 1. So what's a manometer? It's kind of like a barometer. It measures pressure, but it doesn't measure atmospheric pressure. It measures the pressure of a confined gas. So the gas is going to be confined in this vessel right here. And then when you put the gas in, of course, we're going to cap the top of it so that the pressure in here is applied against that mercury. That's what that is. That dark area there is mercury. It's got atmospheric pressure bearing down in opposition. So as long as the pressure inside the vessel is equal to atmospheric, those two levels of mercury will be the same. But notice in this example, they're not the same, right? The flask is over here. They're not showing it. There's a gas in it. And the notice that the mercury is higher on the side of the flask. So what does that mean? That means that the pressure inside the flask is less than atmospheric. Atmospheric pressure here is pushing down, and the opposition to atmospheric pressure is coming from two places. It's coming from this difference in mercury level, and it's coming from the pressure inside the flask. So the question is, with an atmospheric pressure of 717 torr, they're telling you that right at the beginning. Atmospheric pressure one second. Atmospheric pressure is 717 torr. That's the same thing as millimeters of mercury. So the pressure inside the flask is the question. Okay. So what's the total pressure? The total pressure is atmospheric, right? Plus the pressure difference. See, how do we mark that? Manometer. Manometer pressure is 140 millimeters, and this is millimeters. Well, actually, they want the answer in torr first, which is okay. Okay. So the combined flask and manometer pressure equals atmospheric pressure. So this one plus this one equals the atmospheric pressure. Let's see. Oh, we know what this one is, 140. Right. So the pressure inside the flask is 717 minus 140. So I get 577. So this one is 577 torr. All right. So is that what they're looking for? With atmospheric millimeters greater on side of the flask, I think they're looking for. All right, we have to. Are we missing some? Huh. I think they're missing some words in that statement. Let's put that answer in. What did I say? 577 torr. How many atmospheres is that? Well, it's millimeters of mercury, so we divide by 760. Which is 0.759. Right? And they want us to convert it to pascals. Right? So if this is atmospheres, we need a conversion factor for pascals. We know what that is, right? We just look it up, of course. 101,325. So multiply that one times 101,325. So that's, let's see, 4 places. 76,927. I'm not rounding that one off. I guess I could, 3 places. So it'll be 7, let's see, 3 places. 76900. Like that. Now let's see. I like them all. So I think they're missing some words in here because it really wasn't clear. I assumed what they were getting at was what's the pressure inside the flask. Right? So I said, okay, we'll solve it that way. That's the pressure inside the flask, and then the rest is conversion. So does that make sense? If the total on this side is balanced by this difference in mercury plus what's in the flask, then we know the flask pressure has to be less than 717 because part of that pressure is supplied by that mercury column. So that makes sense. All right. So let's go back up here and see what second one says. Maybe it's a little clearer. All right, there's our example again. Now this side, the mercury's higher on the atmosphere side. Okay, so let's work that one. We'll just leave we'll leave these in there. And fill in the values. Okay, there we go. So atmospheric pressure is 789 torr. Pressure inside the flask, we don't know. The difference, the manometer pressure, is 175 torr. Now in this case, the pressure inside the flask is balancing both atmospheric and manometer pressure. So 789 torr plus 175 torr. These two pressures, atmosphere and manometer pressure, are being balanced by the pressure inside the flask. So that's why we want to add those two together. I get 964 torr. So let's put that one in there. They're going to want all three again. Right? Atmospheres. Divide by 760. That'll give you atmospheres. 1.27. Okay. And then pascals. One oh one 325. Okay. 101,325. All right. So I get, let's see, 3 places. 129,000. Let's put that one in. Okay, It liked them all. So the key to these two problems is to recognize whether or not the pressure inside the flask is greater than atmospheric or less than atmospheric. In this case, it's greater than atmospheric. So the pressure inside the flask is actually the combination, or the sum of atmospheric and the manometer pressure. But if the manometer is shifted the other way, then the pressure inside the flask is less than atmospheric, which means that atmospheric pressure is equal to the summation of the flask and the manometer pressure. That's one way to work the problem. The other way, which I thought might be a little more confusing, is to put signs, make positive, negative, right? So you could say this side, call it positive, and if it goes the other direction, you call that a negative, right? But it ends up in the same place. And I think this way is easier to understand. All right. So let's see. Yeah, we're still centered. Let's see. What do we got next? Predicting gas behavior. Okay. This is going to take some effort. I can tell right now. Because select all that apply means that you've got to evaluate each one before you can submit your answer. Okay, so let's see, what are we given to begin with? A glass vessel contains 33 grams of oxygen gas. Mass, 32 grams. 32 grams of oxygen gas. What's the formula? Oxygen gas is diatomic. There you go. And it's a gas. Right. Assuming ideal behavior, which of the processes listed below would double the pressure exerted on the walls of the vessel? So we want to know, for this one, what will double that pressure? What conditions will make the pressure double? All right. First of all, 32 grams of oxygen gas is how many moles? Each oxygen is 16 grams per mole. So 32 grams per mole is molar mass for oxygen. So this is equal to 1 mole. Okay. We may not need that, but it's true. All right. So what do we need to do to double the pressure? One thing you can do is double the moles, right? Avogadro says if you double the moles, you double the pressure, right? So how about this one? 28 grams of oxygen gas. Will that double the pressure? No, because you got 1 mole in there, and that's not another mole. It will get close, but it won't be exact. So that won't double the pressure. All right, let's look at the next one. Raise the temperature of the container from 30 to 60. Right? They're trying Charles' law, right? So what does it take? Well, actually, they're looking at the combined equation. So how would we get double pressure with temperature? Well, temperature is directly proportional to pressure. So if we double the temperature, we should double the pressure. Are we doubling the temperature? No. We're doubling Celsius, but we're not doubling Kelvin. Right? The ratio of 30 to 60 in Kelvin is not 2 to 1. So the second one won't work either. How about adding 32 grams of oxygen gas? Aha, 32 grams is another mole. So this one will work. We double the pressure, double the moles, we double the pressure. That's Avogadro. How about raising the temperature of the container from minus 73 to 127? Okay, we have to decide, is that actually doubling the temperature? Well, we have to convert the temperatures. Minus 73, okay, T1 minus 73 plus 273 is equal to what? 200. Okay. So if we raise the temperature to 127 plus 273, what is that? Let's see, that's 0, and then carry the 1, 0, and then 3, and that's 4. We did double the temperature, did we? Did we not? So that one will also double the pressure. What about adding enough mercury to fill 1/2 the container? What does that mean? If the container's like this, that's volume 1. But if we fill the container halfway with mercury, now the volume is half what it was. So volume 2 equals volume 1 divided by 2. So if we take the volume and we cut the volume in half, that means the pressure has to double, right? They're inversely proportional. That's Boyle's law. So that one will also work right there. Okay. All right. Let's see. Oh yeah, we got oodles of time, I think. What are we doing? We got till 12. 10, 20. We've got an hour and a half at least. Okay. So let's go down to another, this one, and see if it's something new. A gas with a volume of 3.09 liters, a pressure of 1.43 atmospheres, temperature. Okay. Calculate the number of moles. We've done that one before. Find the volume. I bet this was another. That's the ideal gas equation. A sample of 52 grams of neon is placed in a balloon with a volume of 10.3 liters at 25. If 34.1 grams of neon is then added to the balloon at constant temperature pressure, what would be the new volume? Okay, this requires some conversion because you're adding grams. The only way to tell what the new volume is to determine moles. All right, let's do this one. Okay, so what are we given? We've got a balloon with a volume of 10.3 liters. And it's that volume because we have 52 grams of neon in it. We want to know what the new volume is if 34.1 grams of neon is added to the balloon. So what's the second mass? Well, what's already in there plus 34.1? Okay, let's see, what else are we given? Temperature is 25 degrees, constant temperature and pressure. So this is before and after. Temperature and pressure will not change. So we're only concerned with volume and moles. So what has happened to the moles? If we've got V1 over N1 equals V2 over N2, we've got this one, we need to find that one, and we need to convert this one and that one to moles. Right? So this one is going to be what? Neon, 20.18. 20.18 grams. And this one will be added together, also converted. Okay, so N1 is going to be what? Well, we just have to do the math. 52, 20.18 divided into that. 2.58. So volume 1 is 10.3 liters divided by, what did I say? 2.58 moles. And then the second one is 52 plus 34.1. 86.1 grams divided by 20.18. So that's 4.27 moles. Okay? So now we can solve for this one. Take that one, divide it by that one, and multiply it by this one. So I get 17.0 liters. Okay, let's see if the system likes that value. Oops, submit up here. There we go. All right. Okay, and we're still centered, okay. All right, difficulty level 2, here's one. Change in volume of a weather balloon. A certain flexible weather balloon contains helium gas at a volume of 855 liters. That's a lot of gas, but it's needed. Initially, the balloon is at sea level, where the temperature is 25 degrees Celsius and the barometric pressure is 722 torr. Okay. Initially. Then they turn it loose, starts to rise. And at an altitude of 6,000 feet, the pressure is 605 torr, and the temperature is 15 degrees. What's the change in volume of the balloon as it ascends? Get that? What's the change in volume? Not what's the new volume, what's the change? Now, we have to find the new volume to determine the change. But this is a before and after problem. We're given the conditions at sea level and then at 6,000 feet. So let's put what we know up here. Volume of 855 liters. Right, that's when it starts. And the temperature at that point is 25 degrees Celsius. And the pressure is 722 torr. what is the change in volume? So we need to know the volume when it gets there. And then the change is the difference between this one and that one. So what's the temperature now at that altitude at 6,000 feet? 15 degrees. And what's the pressure? Pressure is now 605 torr. All right. So we got some conversions to do first. This one needs to be what? 298 K. This one needs divided by 760. Which is 0.950 atmospheres. This one also. .796. You know what? I didn't need to do that. This is before and after. Right? I don't need to do that. I'm making extra work for myself. I do need to change this one though. All right, so 3 is 8, 7 is 8, 288K. All right. So now, this is going to be using the combined gas law. Did the number of moles change? No. The balloon was filled and sealed. The only thing that changed was volume, temperature, and pressure. So the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Okay, so pressure 1, 722 torr. Volume 1, 855 liters. And T1 is 298 K. P2, 605. V2, we don't know that yet. And then T2 is 288. Okay, so the volume is going to be in liters. That's not the answer. It's on the way to the answer. So to find this one, we resolve this one, and we say that times this, and that divided into that. So 722, 855 times 298 divide, and then 288 times and 605 divide. So I get 986 liters. Right? The change in volume equals 986 minus 855. Hit the wrong button. So that's 131 liters. And there we go. I haven't looked at any of these hints, but I don't even know what they do. Which factor remains constant? Okay. Hint 2. How many moles of helium are in the weather balloon? Oh. It doesn't matter, right? Doesn't matter how many moles are in the balloon. All right. I'm just curious. Volume of the balloon with 33.2 moles. Okay, they're solving the problem in a different way, right? They're finding out how many moles are in the balloon, and then they're converting moles at these new values. So they're making it a hard problem, right? They're using the ideal gas equation to find out how many moles there are under these conditions, and then they're taking those moles and new conditions and determining the volume. Then they subtract. I mean, that seems hard. I mean, that's a lot of extra effort. When you can do it this way, it's a lot simpler, correct? I think so. All right, so let's go back up and see. There's a 2. How about this? 2, density of a gas. That looks interesting. All right, so let's make some space here. All right. Okay, what is the density of carbon tetrachloride vapor at 0.982081 atmospheres and 125 degrees C? All right. So what we're looking for is density. So that's mass per unit volume, right? And the volume they're going for is liters, and the mass they're going for is grams. Okay? So, do we have either one of those yet? Well, no, it looks like it's an unsolvable problem at this point. In order to find the mass of the carbon tetrachloride, we need to know the moles, right? Do we have enough information to find the moles? Well, we got pressure and we got temperature. But do we have volume? We don't have volume. Okay, so here's the solution to this problem. We have to combine equations, right? We have to combine equations. So what equations are there? Well, let's see. We have the ideal gas equation. Right? And we have the molar mass equation. Molecular weight equals mass per mole. Okay? So what are we looking for? We're looking for density. So we need to come up with an equation that preserves density in the final result and combines the others. So if we convert this one to volume, then we can substitute that one in here. Okay. If we convert this one to mass, we can substitute that one in here. Okay, so let's substitute this one in here and this one in here, like that. So density is going to be molecular weight times moles. And this one is going to be nRT divided by P. All right. Now, can we simplify that? Well, yeah. Notice that the moles is here and moles is there. Denominator, numerator cancels. But this pressure is in the denominator of the denominator, which in mathematical terms means pressure is in the numerator. So we have molecular weight times pressure divided by RT. Okay? Now, can we solve this one? Well, molecular weight we can calculate from the formula, carbon tetrachloride. Pressure is given to us in atmospheres. It has to be atmospheres. R, 0.08206. Temperature is 125 plus 273. Okay. So molecular weight. Let's do molecular weight for carbon tetrachloride. So carbon is 12.01. One of them. 4 chlorines. Look up chlorine, 3545. 35.45 times 4, and then add that together. So we have 153.81. Grams per mole. What's the pressure? Needs to be in atmospheres. 0.98208, 982081. 982081 atmospheres. R, 0.08206 liter atmospheres per mole K. And then temperature is 125 plus 273. Okay, there we go. That's the hard part. Now we say 0.982081 times that number. I already had it in my calculator. 0.08206 divided, and 125 plus 273, and divide that into it. So I get 4.63. Grams per liter. Let's see if it likes that. Oops. There. Okay. So that's the way they wanted it solved. They didn't give you enough information to do it stepwise. We needed to combine these equations in order to answer that question. Now that takes some, mental gyrations and a knowledge of algebra and the fact that you can substitute equations. Right? If you have these 3 equations, which are all valid, then you solve them for a term that you want to substitute into one of the others. And that's what we did. My way of thinking, that should have been at least a level 3. I mean, for this course, should have been a level 3. Okay. Gas stoichiometry. Aha. What does that mean? That means we're going to have a chemical reaction. And, okay. It's not giving it to us, so we're going to have to dig a little bit. All right, so let's do that. Let's say, what are we given? 20 liter nickel container. nickel container made out of nickel. Okay. A volume of 20.0 liters. All right. And we're going to put 0.817 atmosphere of xenon gas and 1.32 atmospheres of fluorine gas. Aha. Okay. So pressure of xenon is equal to 0.817 atmospheres. And the pressure of, what's the other one? Fluorine, right? It's F2, right? That's a diatomic gas, 1.31 atmospheres. 32 atmospheres. Okay? And the temperature is 400 degrees. C. The xenon and the fluorine react to form xenon tetrachloride. Oh yeah? I guess so. That's what they say. What mass of xenon tetrafluoride can be produced? All right, so here's the reaction. Xenon plus fluorine, and they're both gases, yield what? Xenon tetrafluoride. Gas. What mass of xenon tetrafluoride can be produced? All right, so let's balance this equation. First, you got to write it, right? And there's the first trick. Fluorine is diatomic. If you don't do that, you're lost. Oops. And then you got to write the products correctly. There we go. Xenon tetrafluoride. Now we can balance it. So we got one xenon. We need 4 fluorines. There we go. Okay. Now we're looking for the mass of xenon tetrafluoride. So that's the question. Mass. Okay. So what do we know about determining the products? You have to know how many moles of the reactants of each reactant. How many moles do we have here? And then once you find the moles, what else do you need to know? Which one is limiting? Right? One of them's going to run out. If you know you've got exact amounts of both of each one. So one of them is going to run out. We got to find the limiting. So first test is to find out how many moles of each one. So we have temperature, we have pressure, we have volume. We can find moles. We need PV equals nRT. So N equals PV over RT. Right? So for the first one, the moles of xenon, we have a pressure of 0.817, a volume of 20 liters, the constant, and the temperature, 273, 673 K. Right? So how many moles of xenon do we have? 0.817, 20, 0.08206, 673. 5. So I get 0.296. 0.296. 0.296 moles of xenon. So we know that we have 0.296 mole here. Okay? Now, how many moles of fluorine do we have? Well, all we need to do, everything's the same except for the pressure. These are partial pressures, right? Partial pressures. 1.32. At the same volume, same R, same temperature. Calculate. 20 times 0.08206 divide and 673 divide. So 0.478. 0.478. 0.478 moles. 0.478 moles. Okay? Now we know how many moles of each gas we have. We can determine which one's limiting. Okay. Normally what you would do is say, this is 1 to 1, so this would produce 0.296 moles from xenon. This one is going to produce half as many, right? 2 to 1. So half of that would be what? .478 enter 2 divide 239. 0.239 moles from fluorine. Right? So that's the limiting one right there. Now we know we have this many moles of xenon tetrafluoride. Right? So we just convert it to mass. Moles, grams. We need molar mass of xenon tetrafluoride. Okay. So xenon, let's look. Xenon is 131.29. 131.29. And fluorine, we got 4 of them, is 19.00. So I get 207.29. All right, times 0.239. I get 49.5 grams. Let's see if it likes that. Okay, we did everything right. So, what are the key stumbling points in this whole operation? Well, first of all, write everything that you know. And then, what's the question? They want to know the mass of xenon tetrafluoride. The only way you can tell the mass is to find out what the reaction is. So the reaction is xenon plus fluorine, gas, F2, that's the first possible problem, yields xenon tetrafluoride. Balance the equation. Now you know that even though you're given pressure, that doesn't help you because you can't go anywhere without moles. You know, I see an alternate solution to this problem, but I don't want to muddy the waters. Pressure and moles are proportional. So we could say pressure, compare the pressure here to the pressure that it would provide over there. Right? So this one would make that pressure over here of that gas. This one would make half that. So half of this would be what? We 0.66 atmospheres. Then you could take 0.66 atmospheres, plug it in PV equals nRT. That would give you the moles of this, which should be that value right there. And then you can convert. So that would have been a quicker way, recognizing that pressure and moles are proportional. So you could work pressure to this side and then convert to moles and grams. But as it is, you want to be sure that this temperature is K. And then when you use you've already got atmospheres, liters, temperature, you can be sure all your units are correct. Okay? That took a little bit of effort. All right. So let's see. Okay, we're still good on time. Let's see about this, a molar mass of a gas. A large flask with a volume of 936 milliliters is evacuated and found to have a mass of 134.66 grams. Okay. Then you fill it to a pressure of 0.967 atmospheres at 31 degrees C with a gas of unknown molar mass. Then you reweigh it, and it gives you a new mass of 136.19 grams. What's the molar mass of the gas? This is a good one. All right. So the question is, what's the molar mass of the gas? So what do we need to know? Mass per mole. We need to know the mass, and we need to know the number of moles to answer that question. So now we go to the information that we're given. All right. The flask is 936 milliliters. Okay. The mass of the flask, empty, that is evacuated, is 134.66 grams. Then we fill it. What's the new mass? The new mass now is 136.19. The mass of the flask plus the gas equals what? 136.19. 136.19. So what's the mass of the gas? It's just the difference of those two, correct? So now we have the mass. We know the mass is the difference here. Let's just go ahead and do that one. 136.19 and 134.66. So that's 1.53 grams. All right. So now we know 1.53 grams. Now all we need is the moles. Okay. What else are we given? We're given pressure and temperature. 0.967 atmospheres. And temperature, 31 C. which will be 304K. All right. And by the way, this is 0.936 liters. Why did I do that? Because we're going to have to use the ideal gas equation. We have to find the number of moles. And that's the only way I know to find the moles for a gas is the ideal gas equation. So if PV equals nRT, then N equals PV divided by RT. The pressure is 0.967. Is that right? Pressure 967, yep. 0.967. The volume is 0.936. R is the usual. And temperature is 304. So there is the number of moles. 0.967, 0.936 times that, 0.08206 divided, and 304 divided. So I get, move the decimal, 0.0363. Moles. So let's divide that into 1.53. So let's see, round it off to 3 places, 42.2. grams per mole. Okay. So the trick to doing this one is, well, actually for any, is what is the question? What are you looking for? We're looking for molecular weight. That's what molecular weight requires. And you say, all right, if I need these two, do I have the information? Right? And you break it down piece by piece. Mass, yep, got the mass right here. Moles, for a gas, the only way to find moles is either before and after or ideal gas equation. And we were given only values for right now that would allow us to use the ideal gas equation. Then you put them together. Okay, so it's a matter of taking a complicated problem and breaking it into small pieces. But before you do that, you got to know what the question is. You got to know where you're going before you create the pieces. Okay, there's another gas stoichiometry. I don't know if we want to tackle another one just yet. This is actually simpler than the earlier one. So let's do this one. Okay, let's see. We're good there. All right, so this stoichiometry problem refers to Joseph Priestley, who was the discoverer of oxygen, and he did it by decomposing mercury 2 oxide. So this is a solid, and he got pure liquid mercury plus oxygen gas. Okay. Now, how did he do it? Well, he took mercury 2 oxide, and he got this monster magnifying glass. It's about 12 inches across. And he focused light on a container that held this compound in it. And he noticed that it was changing. Right? It was actually, you could see it bubble. It was giving off gas. So he collected that gas as it came out of the reaction and tested it. And he also noticed that there was mercury in the bottom of the container when the reaction was completed. Everybody knew what mercury was and what it looked like. Okay. So this needs to be balanced, doesn't it? Right? One mercury, one oxygen. So we could take a half of that one, but we like whole numbers, right? So let's make two of these to satisfy those two oxygens. That means we need two of these. There we go. Now it's balanced. Now let's look at the rest of it. Calculate the volume of gas measured at 30 degrees Celsius and 725 torr that can be produced from the complete decomposition of 3.28 grams of mercury 2 oxide. So we're given 3.28 grams of that. Complete decomposition, producing oxygen. That's the only gas in this reaction. And that oxygen is going to be measured, what's the volume, at 30 degrees and 725 torr. And the volume is unknown. So is this a before and after or a state? It's actually a state. We're only given the conditions right now. So that means you've got to use the ideal gas equation. And to do that, you need moles, right? So we've got to convert this to moles and relate it to moles of gas over there. So this needs to be changed. Mercury 2 oxide. So one mercury is what? Let's see. Where is mercury? Right. Mercury is right over here. 200.59 for mercury. And then one oxygen is 16. So 216.59 goes right here. All right. So we divide this into that. And I get 1.51 times 10 to the minus 2. Moles. Right? How many moles of oxygen does that produce? Well, the ratio is 2 to 1. So this is mercury 2 oxide, and this is HGO down here. That's top, this is bottom, and this is O2. So that's 1, that's 2. So we divide 2 into that. Seven 7.57 times 10 to the minus 3. 7.57 times 10 to the minus 3 moles of oxygen. Now we can solve our equation. Of course, we need this one, 273, and we need this one in atmospheres. And then to solve for volume, then would be nRT divided by P. Right? So the number of moles is 7.57 times 10 to the minus 3. R is 0.08206. Temperature is 30 plus is 303. K divided by pressure. 725 divided by 760. 0.954. There we go. and that will give you the volume. So let's see, I need to divide this one into that one, and then 0.08206 times that, and 303 times that. So I get 0.197 liters. Yep. Volume. 0.197 liters in volume. So let's put that in there, 0.197. And there you go. Let's see, that looks good still. Okay. This one's another stoichiometry. I'm not sure we want to do that. It's just more complicated. So let's move on to something else. Oh, wait a minute. We were at level 2, weren't we? That's why it's more complicated. Shifted to level 3. Collecting a gas over water. All right. A sample of oxygen gas is collected over water at 25 C and a total pressure of 651 torr. The volume of gas collected is 500 milliliters. What mass of oxygen is collected? The vapor pressure of water at 25 degrees is 23.8 torr. All right. So this, I think I described this in class at one time. This is an exercise. Actually, it's a couple of different things. But one thing for sure is Dalton's law of partial pressures. If we collect this gas sample, so there's your water, and here's your container. Say it's a graduated cylinder, upside down. Right? So it's got volume markings on it. It's filled with water at first, and then you collect your oxygen gas like this, right? Like that, and it fills the top with gas. So oxygen gas is moving in here like that. You're collecting it. So what's happening when you do that? Well, water vapor is being deposited in that oxygen gas. So you've got two gases in there. The total pressure is equal to the pressure of the oxygen gas, but also the pressure of the water vapor. Right? So what is the actual pressure of the oxygen gas? Well, first of all, what are we given? Temperature is 25 degrees. Right? Pressure, the total pressure is 651. All right. The volume of the gas collected, the total volume of the gas is 500 milliliters. Okay. What mass of oxygen is collected? Well, in order to do that, we need to know moles. Okay. But we don't want to calculate moles of water and moles of oxygen together, because then we won't be able to determine the mass, because it'll be a mixture. So we need to know the pressure of oxygen here. So in order to do that, we subtract the pressure of water at 25 degrees. Okay. So if the total is 671, and the pressure of oxygen here is that, the pressure of the water given is 23.8 torr, right here. 23.8 torr. So the pressure of oxygen is this one minus that one. Let's see, 647.2. I'm going to keep that extra decimal just for rounding to avoid rounding error. Okay, so now we have everything we need to substitute into the ideal gas equation. We need the number of moles. Okay? So we have PV over RT. Pressure is now 647.2, but we need atmospheres. 760. .852, 0.852. The volume is still 500 milliliters. Why? Because both gases occupy that same volume. Right? So they're equally distributed throughout. We use that volume. That's a half a liter. .08206. And then temperature is 25 plus 273. .298 K. Okay, this is atmospheres. All right, now this gives us the number of moles of oxygen. So I get 14.4 moles. Now we convert that. Yep, they want grams. So how many grams in a mole of oxygen gas? Well, it's O2. So it's 16 plus 16. 32. .459 grams. I'm going to redo that calculation. Yeah, I thought there was something wrong. 0.852, 0.5 times 0.08206 divided and 298 divided. 1.742 times 10 to the minus 2. There we go. Now, times 32. I get 0.5, let's see, three significant figures, 0.557. Oops. I didn't like that. All right, let's see what I did wrong. .671 torr. Oh, 651 torr. That's the problem. All right, it's going to make me try another version. So it's going to give me different values. So I'm going to have to substitute those values in. 654 torr now. Right? And 23.8, that's still right. So now this one is going to be 630.2. 630.2 divided by 760 is 0.829. 0.829 atmospheres. Okay. How about the temperature? 25 degrees, 273 and 25, 98. That's right. That's still the same. Still the same volume, just a different pressure. Okay. So let's recalculate the number of moles. Uh, 1.70 times 10 to the minus 2. And let's see, let me keep all my decimals. 695. 695 times 32. 0.542. There we go. Let's try it again with our new pressure. There we go. So, I had to recalculate it for the different version because I missed the first one. All right. Now, let's see, what else? Level 2, characteristics of gases. Let's skip that one. We did one like that before. Partial pressure. 25.5 grams of argon neon at these temperatures. Total pressure of the tank is this. Calculate the partial pressure of each gas in the mixture. All right. We can do that. Shouldn't take too long. So we're given 20.5 grams of argon gas. Mass of argon equals 20.5 grams. And the mass of neon is 6.76. Okay. The temperature of both gases is 27 degrees. Okay. And the total pressure is 6,329 torr. Okay. What they want to know is, what is the partial pressure of each gas in atmospheres? So we're going to need to know the number of moles of each one. Right? You can't do any of these calculations with mass. We need to know moles. So we got to convert argon to moles, which would be, right, times that one, So what's argon? Argon is 39.95. So the moles of argon equals 20.5 divided by 39.95 is 0.513. In a second. Beatsy. Come on, Beatsy. You need to go out. Come on. Come on. All right. Neon now. So this one, we need the molar mass for neon. And that would be 20.18. There we go. So the moles of neon will be equal to 6.76, enter, 20.18 divide is 0.335, 0.335 moles. Now we know the moles of each one. The internet problems. The total pressure is 6329. And the pressure that's attributed to each of them is based upon the mole fraction. What fraction of the total moles is this one? What fraction is this one? Right. So the mole fraction of argon is equal to 0.513 divided by 0.513 plus 0.335. Okay. That's the mole fraction of argon. So that's 0.605. 0.605. And the mole fraction of neon is 0.335 divided by this same total. All right. .395. Now, what do we know about mole fraction? If you've accounted for every gas in the container, then the sum of all the mole fractions should be equal to 1. So this one plus that one should be 1. 5, 1, yep. In fact, it is equal to 1. Okay, now the pressure attributed to this one is that one times the total. So we need to multiply this one times the total, which was 6329. 6329. .605. Sure. 6329 times is 38294. And this one times 6329. Well, actually, this one ought to be that one subtracted from the total, but we'll do it this way, just to be thorough. So that one, 6329, is 2500. Okay, we have these two together, it should be 6329. So that's 3. Yep. Okay. But they want the value in atmospheres. So we got to divide this one by 760. Which is 5.04 atmospheres. And this one, divided by 760, is 3.29 atmospheres. Now we can put those values in and see if we got it right. So for argon, 5.04, and for neon, 3.29. And it liked my answers. Okay. So this is a lesson in Dalton's law of partial pressures, because the total is the sum of the two. But we only know the sum of the two based upon the fact that mole fraction is proportional to the pressure. The mole fraction of 1 tells you the pressure, its partial pressure of the total, and similarly for the neon. All right, let's see. Looks okay. All right, let's see, 11:30. So we got what? Another half hour? No, we got 20 minutes. Okay, so we're still on level 2. Let's see if there are any level 3s down here that would give us a challenge. There's a 3. Okay, this is a stoichiometry problem. Yeah, we've this is collecting oxygen over it's more complicated, but it's still similar to that Priestley problem. Okay, let's look for another one. Let's see. Yeah, that's another one. I'd like one that's just a little simpler than that. We could do that one. Let me hold 089. We might come back to that just a second. Let me see what else is down here. Ooh, there's a 4. Carbon dioxide gas saturated with water vapor can be produced by the addition of aqueous acid to calcium carbonate. How many moles of carbon dioxide collected at 60 degrees? Yeah, okay. Sulfur trioxide is produced in enormous quantities each year for the use by this reaction. What volume of O2 and a pressure is needed to completely convert? Okay, this one is difficult because you've got 2 reactions going on at the same time. You've got oxygen for this one and you've got oxygen for that one. So I don't think that's one that I'm gonna impose on you guys. That one's is given a difficulty level simply because there are 3 parts to it. It's really not that difficult. I mean, you've got pressure, volume, moles. Solve the ideal equation for temperature. So that's it. I don't think that's a difficulty 4. Okay, we might be have exhausted everything that we need. Let's take this one look at this one. Sodium bicarbonate. Heated sodium carbonate is produced with the evolution of water vapor and carbon dioxide gas. Okay. What total volume of gas measured at 27 and 678 is produced when 1.5 grams of this is completely converted to sodium carbonate? That might be interesting. Let's do this one as our last problem. 13.143. I think I need a new marker too. I can get it working. There it goes. When they've been sitting for a while, they don't want to cooperate. Okay. So our equation is this. Sodium bicarbonate, solid, is decomposed to sodium carbonate, solid, plus these 2 gases. And CO2. I have my general chemistry class do this reaction in the lab. They actually heat sodium bicarbonate and produce this solid, but we don't capture the gas. They have to speculate on what the gases are. But that's neither here nor there. Okay, what total volume of gas? So we want the total volume of gas. That's the question. And the conditions are 27 degrees C, temperature 27 degrees C. Let's see, 678 torrs the pressure. All right. It's produced when 1.5 grams of this, 1.50 grams, is completely converted. Okay, so this is a balanced equation. You can see 2 sodiums, 2 carbons, 1 there and 1 there, and 6 oxygens. So 3 there, 4, 5, 6. So it's balanced. Now, how are we going to answer this question? Well, we have temperature, we have pressure, we want to know volume. So if we're going to use the ideal gas equation, we need moles. So we need total moles of gas. Right? So we need to convert this to moles, and then this to that many moles and that many moles, and add them together. Right? Because the ideal gas equation doesn't care what the gases are. It just wants to know the total. So how many moles is that? So we need the molar mass of sodium bicarbonate. So sodium is 23.0, and hydrogen is 1.01, carbon is 12.01, and 3 oxygens. So that's 48, right? 16 times 3. So I get 84.02. Right? Divide that into 1.5, excuse me. 1.785 times 10 to the minus 2. 1.785 times 10 to the minus 2 moles of sodium bicarbonate. Right? So if the conversion is complete, then how many moles of water are you going to get? We get half that many, right? Right? 2 to 1. How many moles of carbon dioxide are you going to get? Half that many, right? So half of this is here and half of this is here. It's equal to that in many moles. So that's the total moles of gas right there. So now we can solve. Let's see, PV equals nRT. Solve for volume. Volume equals nRT divided by P. Right? We need pressure in, well, let's see, moles we got 1.785 times 10 to the minus 2, R 0.08206. Temperature, 27 plus 273. 300. Okay. And pressure, 678 divided by 760. 0.892. Atmosphere. Right? So that gives us the volume in liters. All right. So let me see. I need divide that one and then times this one and then 0.08206 times. So I get 0.493, 0.493 liters. I'm going to check that again because the last problem, when you got kicked off, the last problem, I made a calculation error and had to redo the whole thing with different values. So I'm going to check this one before I even put the values in. 1.785 exponent 2 minus, okay, 0.08206 times 300 times, and divide by 0.892. Okay, we're good. So that's the volume, 0.493. Liters. There it is. Okay, that's about all we have time for today. So we'll what we'll do, let's see, what day is this? Tuesday. Thursday we meet again. Yeah, Thursday. Thursday we'll look at the review document contained in Blackboard and work from that. So take a look at that one, the review document, and work as many of those problems as you can, and any of them that are giving you trouble that you can't solve on your own, bring them to class and we'll deal with them first. Okay, well, that's it for today. I'm going to stop the share and say goodbye. See you in a couple of days.